So this is my chapter 9 exam for my physics class, and the question I picked was question 3 because 3 is one of my favorite numbers. So I decided just to pick this one. And the first question, let me read what the question is. It says, an electric fan is turned off and its angular velocity decreases uniformly from 460 revs per minute to 250 revs per minute in a timeline of length 3.65 seconds. And then for question 1, it says, find the angular acceleration in revolutions per second and per second. So the given values are, let me write it out. These are the initial angular velocity equals 460 revs per minute. And then I would have to do, then I would do 460 times 2 times pi over 60, which equals 41.71 rads per second. And I did that is like to break it down, so it's just easier to use this. And then for the final, angular, that equals 250 revs per minute. So you can see, and then I'm gonna do the same thing like here, but with the 250. So 250 times 2 times pi for 60 equals 26.179. Oh no, that's not. There's rads per second. And then t equals time interval. This is just all the given information, which equals 3.65 seconds. So now what I would do, and now I have to use the first rotational kinematics equation just to find part A, which equals work F equals work I plus angular T. Now I'm just gonna, and now I would bring over the angular to have by itself. And then I would bring over, subtract the WF and bring it over to this side, and then I just have the angular equals work F minus work I over T. And now I would plug in the numbers I got. So I would plug in 26. So I'll put the work, WF is work final. So the final is 26.179 minus, because I brought off the WF. So subtract minus 48.171 over T, which is time, which is 3.65. And then I get negative 6.025 rad per second squared. And then since 1 rev equals 2 pi, so now I would do negative 6.025 over 2 pi, which equals negative 0.959 revs per second squared. And that's the answer I got right here. And then part B, it says, find the number of revolutions made by the fan blades during the time that they are slowing down in part A. So now, this is for 3A. And then 3B, I would just use the second kinematics equation, which is theta equals work IT plus 1/2, parentheses 1/2, and then times angular T squared. And now I'll plug in the numbers I have. So let's put equals theta equals 48.171 times 3, because it's the initial times the time, times 3.65. And then I gotta do plus the 1/2, and then times then negative 6.025 times, run out of room, so I'm right over here, 3.65 squared, because t is 3.65 is time, and I have to square, and the angular is negative 6.025. So, and I plug that in, then I get equals 135.7. And then still, since, so you can see 1 rev equals 2 pi rad. So I would plug in 2 pi. So I would do 135.7 over 2 pi, which equals 21.6 rev. And that's what I got right here. And then for part C, it says, how many more seconds are required for the fan to come to rest if the angular acceleration remains constant at the value calculated in part A? So for 3C, I would do, it says I'm gonna use the first rotational kinematics equation to find time required by the fan to stop. So I would plug in work 1 equals work 0 plus theta t, not theta, angular t times angular t, and then I would bring over, I would subtract the work 1 and bring it over to here, and then I would divide the t over everything. So then this was what it would look like. It would equal t equals, oh, not the t, I would divide the angular over everything. And I have t equals, because t's by itself now, work 1 minus work 0 over angular. So, and then, so I know the numbers, so work 1 will equal the final angular speed of the fan, and that equals 0 rads per second, and then work 0 equals initial angular speed of fan, and that equals 26.179, And now I just gotta plug in these two numbers, and t equals 0 minus 26.179 over negative 6.025, because that's the angular. And then what I get from that is 4.35 seconds.